Today we're going to talk about the role of electronic configuration in bonding and a little bit about ionic bonding. Specifically also we're going to talk about polyatomic ions and how they are also covalent and ionic bonds at the same time. First, I thought we'd look at some electron configurations and some orbital diagrams, and what we're doing is actually looking at period 2 of the periodic table. If you look at period 2, this goes from lithium all the way over to neon. You see, remember what we said, that electron configuration is stable when you have a filled S and P sublevels. So let's look at, if you see anything that's on here that's filled. If you do, hopefully you see that neon is the one that's filled. So for neon, you notice its outer valence electrons would be the 2s and the 2p. So that gives us 8 valence electrons. Now these we're not concerned about because that's part of your core electrons. These 8 outer ones are involved in bonding. So neon's stable. It doesn't really form any bonds because these outer sublevels are filled. And so when we draw neon as a Lewis diagram, we do 2 dots that would represent, so I put 2 dots there that would represent the S, and then 2, 4, 6 dots that represent these 3 different p orbitals. So neon is fine, doesn't form any bonds. Now, what do the other electrons or other atoms do to form stable compounds? Well, what they do, I mentioned, is they form compounds. And to do that, they form ions. For example, lithium will typically form a lithium plus ion. So that means it loses 1 electron, then it has a stable 2s. Beryllium can be 2 plus, will lose these, and become 1s2. Now, the other things we see are things such as nitrogen. Nitrogen, notice it's 1s2, 2s2, 2p3. 2p3 is not stable, so what it does, it actually, instead of losing electrons, it gains 3. So instead of 2p3, we have 2p6, and we add an electron into that orbital, and that orbital. So nitrogen gains 3. Oxygen, so that's nitrogen, goes to 3 minus. Oxygen, you should remember, goes to 2 minus. It needs to gain 2 electrons to become stable. So it goes to 2 minus, and instead of 2p4, it goes to 2p6. So we put an electron in this orbital, electron in this orbital. Now notice it forms this when it's part of a compound and it's gained those electrons from, of course, a metal. Now fluorine becomes F minus. It's the most electronegative element that there is. And what it does, it gains 1 electron here, and it becomes 2p6. And this 1 electron goes in this orbital right here. So all of these are stable, but notice every single one of these has a configuration of neon because they've gained electrons. Notice lithium has a configuration of the previous noble gas. So let's keep going. So a stable configuration is when you have a full S and P sublevel, so you have S2 and P6, so you have 8 valence electrons. Now this is for most things. Notice lithium, if it's one of the first elements in the periodic table, it may have a 2s configuration. But for most things, it's going to be 8 valence electrons. Let's look at some metals. So, for example, sodium we know has 11 electrons. So if you do the electron configuration for sodium, it should be 1s2, 2s2, 2p6, 3s1. So notice when sodium forms an ion, what it simply does is it loses that 1 3s electron. So that one right there is lost. So instead of sodium with 11 electrons, sodium ion has 10 electrons. And its configuration is just what we see above, but we've lost 3s electrons. So now we've got 1s2, 2s2, 2p6. Now if we go one further, what this is actually, this has a noble gas configuration. What noble gas has this configuration? What should be the noble gas that's prior or previous to sodium, and that would be neon. Now let's look at a nonmetal. Let's look at phosphorus. Phosphorus has 15 electrons. If we do its electron configuration, this would be 1s2, 2s2, 2p6, 3s2, 3p3. These are the valence electrons. Now, nonmetals tend to gain electrons, so these are going to be gaining electrons to form, give a full electron configuration, or 8 electrons in this outer orbital. So what charge do you think phosphorus will have when it gains a charge? Look at the periodic table, see if you can figure out its charge. Phosphorus should get, hopefully you got this correct, would get a 3 minus charge. That gives it 3 extra electrons, for a total of 18 electrons. So those 3 extra electrons will go specifically in the 3p orbital, whereas prior to this it was 3p3. Now the electron configuration has gone to 3p6. Now notice your valence electrons are simply this highest number, which is number 3. So now we have 8 valence electrons in our outer sublevel. What noble gas has this configuration? Notice for nonmetals you'll pick the one subsequent or after the nonmetal, and this would be argon. Another thing we want to talk about today is forming anions and cations. Cations are positive, just a name for a positive ion, and anion is just a name for a negative ion. So metals form cations by losing electrons to achieve the previous noble gas configuration. An example of this, calcium goes to calcium 2+, and it loses 2 electrons. Now notice we wrote the electrons on the right-hand side. That means the electrons were lost. And notice that this, when we wrote this, it's balanced in 2 ways. We have the same number, we have 1 calcium on each side, but notice it's charge balanced as well as atom balanced. There is no charge on the left-hand side, but on the right-hand side, the product side, if you had a positive 2 and a negative 2, you end up with a 0, so it's balanced for atom and charge. Whenever you write a reaction, even if it's losing or gaining electrons, please always make sure you balance it for atom and charge. So we notice when we write this reaction that lost electrons are written as products because they are given off. Okay, so that's very important. Metals lose electrons, and that's why metals have positive charges. Now, nonmetals, on the other hand, form anions by gaining electrons to achieve the next noble gas configuration. For an example of that, let's look at chlorine. Chlorine gains 1 electron and becomes Cl-. Now notice that electron here is written on the left, so it's a reactant. So what we're going to say here is gained electrons are written as reactants because it's gaining the, so gaining means we're putting it on the left side, so we're adding it to the atom. So that's an important distinction between metals and nonmetals. Metals, of course, form cations or positive charges, and nonmetals tend to form anions which have negative charges. So the last thing I want to do is throw in polyatomic ions. We did have a few of these in the lab today. Now polyatomic ions are interesting because they are part of an ionic compound. So if you have a polyatomic ion, you will have an ionic compound. You do not have polyatomic ions by themselves. They're part of an ionic compound. But the polyatomic ion itself is held together by covalent bonds. So it's important to see that it has both characteristics. It is a part of an ionic compound, but within, and I think maybe that should be the distinction we make here, within the polyatomic ion, there are covalent bonds. Now you see this is a phosphorus surrounded by 4 oxygens. Each of these lines represent what we call a bonding pair of electrons, and then we have our lone pairs. So there you have your bonding pair, and you have your lone pair in this polyatomic ion. But notice it has a -3 charge. That means that this is going to form an ionic compound with something that's going to have a positive charge to equal that out. Let's look at a couple other polyatomic ions. Let's look at, hopefully you recognize this as hydroxide. Hydroxide is OH-. In a hydroxide, it's oxygen and hydrogen atom bond together. So here we have one bonding pair of an electron. And here we have 1, 2, 3 lone pairs. So notice we're following the same rules you learned with bonding. We have 2, 4, 6, 8 electrons around oxygen. We have 2 electrons with hydrogen, so it has a duet, it's happy. Oxygen has an octet. Notice the entire thing is -1. There's not a partial negative charge anywhere. This is a true ion. So to represent that distribution of that charge throughout the entire particle, we put brackets, and the negative charge goes outside the bracket to show that it's not just with the hydrogen, it's not with the oxygen, it's equally surrounded. If you were to count the number of protons in this particle, and we can do this, there's going to be 1 more electron than proton. So the number of electrons is greater because we've added an electron to this. Before we added this electron, it was a neutral particle. So this would be hydroxide would be part of an ionic compound, but the hydroxide particle itself has a covalent bond within the polyatomic ion. Let's look at one more. I want to show you this because this is a positive polyatomic ion. There's only really 2 positive polyatomic ions we'll use. One is this one, which is called ammonium, and the other is a mercury 2, which is Hg2, 2+. In ammonium, you have one nitrogen surrounded by 4 hydrogens. Notice that we have, in this one, we have 4 bonding pairs, no lone pairs. And the entire particle has a +1 charge. Now the reason it has this charge, if you were to count the entire number of protons and the entire number of electrons, this would have 1 less electron than the number of protons in this. And you could do this if you had a periodic table handy. And maybe I should stop and grab one. Okay, so here we're looking at, I've got a periodic table here, so here we're looking at ammonium. Ammonium, if you look at it, each hydrogen, so there's 4 hydrogens, so if you look, it's NH4. So let's count the number of protons we have here. So nitrogen is atomic number 7, so it has 7 protons, and then there's 4 hydrogens. So altogether, that gives us 11. So it has 11 would be the number of protons. But the number of electrons would be 1 less from this. So that means we actually have 10 electrons because we've taken away 1 from the total. Before we took 1 away, it was neutral, but now there's one less electron. And so that's why this has a +1 charge to it. So ionic bonding. So ionic bonding can be a combination of a metal and a polyatomic ion with another metal, non-metal polyatomic ion. Now notice the first one that's written always has to be a metal or a polyatomic ion. Now the second one that's written can be a non-metal or a polyatomic ion, and this will make more sense as we go through the example. So for example, lithium, that's lithium without losing an electron. It loses 1 electron, becomes lithium +1. And then you could have calcium 2+, that's a calcium ion, or you could have a polyatomic ion, which is such as ammonium, which is an H4+. So let's say lithium combined with a fluoride atom, and fluoride would be a -1 charge. The formula for that would be LiF. Notice the positives and the negatives equal when you have the formula of the compound. Let's say you have calcium combining. Let's say calcium combines with a hydroxide. This is hydroxide, we said, is a polyatomic ion, so it forms an ionic compound. You have to even out your negative and your positive charges. We need 2 negatives to equal that 2 positive. So the formula for calcium hydroxide would be Ca parentheses OH in parentheses 2. And ammonium as well could be involved in ionic bonding. For that, it would have to bond with another negative ion. So let's say ammonium combines with phosphate. Now we're going to have more ammoniums than phosphate because phosphate's bringing in a 3- charge. So if you wrote the formula for ammonium phosphate, it would look like this: parentheses NH4 and parentheses 3 PO4. So this is a little brief summary of how polyatomic ions are involved in ionic bonding, and how they contain covalent bonds, and as well we talked about the role of electron configuration and stability in forming ions. And if you have any questions, that's it. We'll be working on this tomorrow.